Hi guys, let's do minimum depth of binary tree. So we're given a binary tree and they want us to find its minimum depth, and they tell us that the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node, and a leaf is a node with no children. So in this example, we are given this tree and we would output 2 because as we can see, the minimum depth here would be 2 with nodes 3 and 9. And in example 2, I don't know why they don't show us the diagram, but if we go over here to look at it, we would return 5 because the minimum depth is this path with all of the nodes in it with 2, 3, 4, 5, and 6. Because there's nothing to the left, so we don't count that. So if we think about our base case would be if the root was null, then we would just return 0 because there's no nodes in there, so there can't be any depth either. But beyond our base case, what we are doing, so we need to explore each path. So we're going to need to do DFS because we're exploring each path all the way to the end to even find what the depth is of each path. And then we need to compare them to each other to find the minimum one. So like first we would go down here and then we find that this has a depth of 2. And then we would go down here and find that this has a depth of 3. And this one has a depth of 3, and then we would compare them to find the minimum. So let's do our base case first. So if our root is null, then return 0 because there's no height, or no depth, sorry. And then if we, so actually let's take another look at this example over here, where we just have them all in a row. So if we start at 2, let's say, which is the root, then in this example, we can only explore the right subtree because there's nothing to the left, right? If we try to explore root.left, that gives us null. And so we don't want to go that way. But we also don't want to just take this as the minimum depth either because that doesn't count, right? It doesn't count unless there's actually nodes on both sides. So if root.left is null, then we're only going to want to explore the right subtree. So we're going to return, and then we're going to recursively call this method. But we're going to add 1 for the height, or for the depth, sorry, because we're counting this node as 1. So we're going to add 1 and then check the depth again, starting from root.right, if that makes sense. So min depth root.right, and let me double check that okay, yeah. And then same thing for the other side. So if root.right is null, then we're going to return 1 plus min depth of root.left. So does that make sense so far? Because if there's no node in, if we're checking root.left, for example, in here, then we get null, right, which we see in here. And so we don't want to count this. So we add 1 for this node's depth, and then we call this method again using root.right. And so then 3 would be our new root. So then we have 1 plus this subtree, and then we're going to do the same thing again. So the root.left is null. So then now we add 1 to our last call, which was 1. So we have 2 plus then this subtree starting from 4. And then root.left is null again. So then we have 1 plus 2, which is 3, because this is our third node now. So 3 plus this subtree, because then we're going to call it again with root.right, which would be 5. And then we have 1 plus 3, which gives us 4, and then 1 plus 4, which gives us 5, and then we would reach the end, and then we get root.null. Or root.left and root.right is null, and then we would exit. So, yeah. Okay, then this is not the case, so if both of the nodes exist, so root.left is not null, root.right is not null, then we are just going to return 1 plus, and that would be this original, example 1, where we have nodes on both sides of the tree. So we would want to explore both of those sides and just get the minimum of them, right? So this one would be 2 and this one would be 3, and then we would take 2 because 2 is smaller. Then we're gonna explore both subtrees, but we're going to take the minimum of each subtree's depth. So 1 plus math.min to get the minimum, and then we're going to call min depth on root.left and min depth on root.right, and we're going to take the minimum of those two and add 1 again for our current node in each call. So that should be it. And then our time complexity is O of n, where n is the number of nodes in our tree. And that is because we need to explore and visit every single node in the tree, whether it's full like this or whether it is... Okay, well now it's not showing me the diagram anymore, but whether it's like example 2 where it was like all in just one line, we still need to explore every single node to be able to find what the depth is. So yeah, that's O of n, and then our space complexity is O of n, where n is also number of nodes in the tree because we need to add every single node under our call stack. So if you guys are sensing a pattern here, typically when we're doing trees, I think a lot of the time time and space complexity are both going to be O of n because we're going to have to visit every single node, and then when we visit every single node, we're going to have to add every single node onto the call stack, at least for DFS. But yeah, that was it for this problem. Thank you guys for watching. Like and subscribe if you found this helpful. Bye.